Welcome back to che531. In this video, I'll be talking about numerical solution of ordinary differential equations. This is page 120 in lecture notes. So before we start talking about how we can solve differential equations numerically, I'd like to go over some sort of definitions of terms that we're going to use throughout this part of the course. The first thing is about initial conditions. So when we talk about initial conditions, that is usually when we talk about time-dependent differential equations, and the condition at t equals 0 usually is called initial conditions. Okay, so another thing I want to talk about is the transient problems. If you have a problem which is time-dependent and the solution varies with time, this is called transient problem, again, because the response of a system varies with time. If the response of a system does not vary with time, that is called steady-state solution. That means something that doesn't even change with time. Okay. Ordinary differential equations are the equations that are involved with only one independent variables, like x or y or z. So you cannot have like two or more independent variables. If you have a differential equation with let's say x and y as independent variable, that is called partial differential equations. So for ordinary differential equations, we only have one independent variable. Okay, the partial differential equation, as I said, if you have more than one independent variable, then that is called partial differential equations. For instance, if you have like a function of x and y, or x, y, and z, then that is partial differential equations. Other term is implicit equation and explicit equation. So in implicit equation, we have the unknown on both sides of the equation. Let's say in this case, y is a function of x. So I'm looking for y as a function of x, but y shows up on both sides of the equation. And I cannot really have an equation where y only shows up on one side, like y equal to something, and that is only a function of x. If you cannot find such a thing, and your unknown, in this case y, shows up on both sides, then that is called implicit function. This is in contrast to explicit function, where the unknown shows up only on one side of the equation, like y equals ax plus b, and you see that y is only on one side. I do not have any other term that is involved with y. Okay, so in other words, I can basically isolate y on the left side and move everything to the right side, which is only a function of x or constant. Okay, that is for explicit. For implicit, you can't do that. I mean, you see that y is on the left side, but also you have a function of y on the right side. Okay, so we're going to move on to the first numerical scheme for solving ordinary differential equations. And we're going to start simple by looking at first order ordinary differential equation. First order, that means we only have first derivative of the independent variable in the equation, like dy dx. We do not have d squared y dx squared or so. Okay, so that is about first order. The first method we're going to look at is explicit forward Euler, or explicit Euler. So we're going to start from a generic form of a differential equations. We have, let's say, dy dx, and y is a vector now. Could be y1, y2, y3. We can have multiple y's in there. So we just lump them as a vector. Like you have a differential equation which has like the concentration of some species unknown. You can have the temperature unknown. You can have like the volume unknown. And all of these could be function of something else, like the pressure or something else. So we lump all the unknowns into the y vector, right? So my y now includes y1 all the way to yn. So we're going to start very generic with n possible y in the vector. Now on the right side, in a generic form, we can have x and y. So basically this is going to be implicit form. You see there's y's on this side as well as on that side. Okay, but in terms of the derivative, it's explicit. That means the derivative only shows on the left side and no derivative is on the right side. Okay? Alright, so we're going to approach this problem using forward Euler. So Euler proposed that we can basically approximate this derivative by some sort of tangent or like secant line. I can say that like the derivative at any point is nothing but the slope of a tangent, and the slope of the tangent can be approximated by the slope of a secant. The slope of a secant can be calculated using 2 points, right? If I have 2 points, y1, well, let's say yi, or yi plus 1 and yi plus 2, or yi plus 1 and yi, you can basically find the slope between these 2 points and say approximately this is slope. It's pretty much like the slope of a tangent at point I. So I'm just showing here the y-axis and then the x-axis with like the black line is the curve that I'm looking for, and the red line is the tangent to the curve at point I. Okay. So according to the Euler's method, we approximate the derivative by subtracting the y at the next x value. Let's say if I'm looking at this point xi, the next x point in this along the x-axis with the same interval of delta x or whatever, then the next one is going to be xi plus 1, whose y is also yi plus 1. Okay, so if that's the case, the difference between the two y values, which means this height, divided by the difference of the x values, which is this base. So this height divided by this base gives you the tangent to this secant line. And I would say this is approximately equal to the derivative, because that's pretty much like the slope of the tangent on xi. And so, so right here we say yi plus 1 minus yi divided by del x is equal to the function evaluated xi yi. Okay? So in here, we assume that everything is known except the higher index, the higher index variable, or the variable with the higher index yi plus 1. Because that's the only unknown, we move all the knowns to the right side. So our function now is going to look like yi plus 1 equals delta x times f plus yi. So from here, if we know everything xi and yi, we can basically solve for yi plus 1. Now we have yi plus 1, we can go to I plus 2, knowing that we know everything up to yi plus 1. Then we solve for yi plus 2. Now we move on to the next step, which means I plus 3, assuming that everything up to yi plus 2 is known, and so forth. So we can see that this progressively starts from the left side of the x-axis and goes to the right side and basically detects this curve, which is nothing but the solution to the differential equation. So as an example, let's try to solve this using forward Euler. I have a function, a differential equations with 3 unknowns, y1, y2, y3, whose derivative is equal to this crazy vector function. It's a function of y1, y2, x, and everything is in here. So because that's first order differential equation, we need one boundary condition. Okay? And the boundary condition I'm having here is I know y1, y2, y3 at x equals 0. Let's say all of them are 1. Assuming that delta x is equal to 0.1, we're going to go and solve this differential equation. Okay? So I'm going to switch to MATLAB script and show you the script for this. Okay? So we're going to look at the first approach, which is forward Euler or the explicit Euler method. So these are the logistics. Clear the screen, clear all the variables, close all the figures. Now we're going to introduce a function. In this function we have three elements. The first one is this term, x, y, y1, y2 divided by y3. And that's the same thing, x, y1, y2 divided by y3. And the second and third one are also the same as these two. So this is basically the right-hand side of my f function. So here's the right-hand side. Basically, I just lump them into this f as a function of x and y. Maximum iteration set to 100. I initialize everything to 0. The initial or the boundary value was at x equals 1. I'm sorry, at x equals 0. So when x is 0, my y is 1, 1 is 1, 1, 1. Okay? Alright. So now, assuming that I want to solve this up to x equals 0.6, my domain length, let's say, is 0.6. And actually, this is not number of iterations, this is number of intervals. So with 100 points along this interval, I discretize my L, 0.6, to 99 points. I mean, 100 points including boundary points means 99 intervals. So the number of intervals is going to be 99, and then L divided by that is going to give us the delta x. So here is the forward Euler. I'm saying that yi is equal to yi minus 1. So you see that this is I minus 1, and on the right side everything is I minus 1. Okay, so I'm saying that yi is equal to yi minus 1 plus del x times f f evaluated at xi minus 1 and yi minus 1. This is pretty much exactly like I say yi plus 1 is equal to yi plus del x times f at xi yi. You can crank up the index I by plus 1 or minus 1. The same equation still holds. In the notes, I have actually I minus 1 version of this, but it's the same thing as this. And the reason is because I start my iteration counter or the loop counter as 2. So if I have 2, then I can calculate y2 in terms of y1, and then y3 in terms of y2, and so forth. Okay, you can start your iteration counter as 1, but if you say so, then this should be I plus 1, and this should be I, this should be I, this should be I. Now after we calculate y, we have to crank up our x to get to the next x value by delta x. So then we say the next x, or xi, is equal to xi minus 1 plus del x. Now here I'm storing all the 3 y values as a column vector, and then every column corresponds to the every I iteration. Okay, so remember my function is 3 unknowns y1, y2, y3. At every x value, I calculate these 3 and then put them in a column vector. And then for the next column, I calculate these 3 for the next x values. Okay. So this is pretty actually simple. It's just like 2 lines of a loop to calculate the y values given the boundary value at x equals 0. Okay, so the rest of it is just to plot the function. So I'm going to plot my y as a function of x. Now remember I have 3 y's, so I'm going to put them into subplots. So I'm using subplot here. I split my subplot into a matrix of 2 by 2. I'll show you in a minute. And for every y, I just pick up one of the subplots and plot the value in there. I have the x limit, y limit, between 0 and L, which is 0.6 right here. And then y limit, which is between 1 and 10. X label. For x label, I'm using the italic x, and I'm using, I italicize it using the interpreter LaTeX. So if you do that, then actually italicize your x value. And then I also make a label for my y. I create a label using this string print function. So this is string print function. And I again italicize it using the interpreter LaTeX. I think that's the end of it.